Okay, I guess we had some homework today. I just passed some back. Were there any questions? I think it was pretty straightforward. I think you had to do some like syntax trees and stuff.
Yeah, I ran out of room, so it goes to the side.
Yeah,
but
whatever.
I think you can get it.
Good. All right, so today now we will learn the second technique for specifying the syntax of a language. Remember, the first technique the first method for specifying this for the syntax of a language was grammars. And review time. What are the four parts of a grammar?
The non-terminal.
Non-terminal alphabet,
The terminal.
terminal alphabet,
The production.
set of rules of production, and the start symbol, which is a what?
Non-terminal.
Which is a non-terminal. And so we saw how to do, and what is a context-sensitive, what is a context-free grammar?
It's always non-terminals.
On the left side, always a non-terminal on the left side of a production rule.
Mm-hmm.
And so a context-sensitive grammar is a grammar that is not context-free. Okay, now, but today we're going to learn a different technique for specifying the syntax of a language. Maybe we should point out one thing here. This technique, which uses finite state machines, is not as powerful as a grammar. So what do we mean by not as powerful as a grammar? There are some languages whose syntax you can specify with a grammar, and it's impossible to specify that syntax with a finite state machine. Do you see what I mean? On the other hand, the converse is not true. For example, every language that has a syntax that can be specified with a finite state machine, it can also be specified with a grammar. So just remember that, and we'll come back to it. And we'll come back to it and we'll give some examples. Oh, actually, that train of thought makes me think of one more thing that I want to go over before we go on. Let's come back and look at figure 7.9. This is the syntax tree for a valid C++ statement, right? And you did a similar one for your homework. And actually, what the compiler has to do is it doesn't start with statement. It starts with, do you remember what the start symbol was for the C++ language?
Statement?
No, the very first, the start symbol is one of the non-terminals. Do you remember what it is? It's back here. It's the very first one here. It's a translation. Actually, the translation unit is the start symbol. So whenever you put your C++ program into the compiler, it starts with a translation unit, and your stream of characters, it parses your stream of characters from the translation unit start symbol. That's what it does. And here's the question that I want to ask. When you look at these rules of production for the C++ language, what do you conclude about this syntax as specified by the grammar? Is it context sensitive or context free? So here's the big question. Is the C++ language context sensitive or is it context free?
Context free.
Yes. Well, now here's why we're discussing this. It would appear that the grammar of C++ is context free. And we can do that by inspecting the production rules. The production rules always have a single non-terminal on the left-hand side of the production. However, I'm here to tell you that in actual fact, C++, the C++ language itself, not just the syntax as specified by the grammar, but the C++ language itself is in fact context sensitive. And why is that? Well, I don't want to go through and give you a specific blow-by-blow description of this, but let me see if I can convince you. Do you know whenever you have a function and it looks like this, suppose it's like int, and it's like my function. And then in my function, you might have something like int n, comma, double y, like this, and then etc. Okay? Now, what parameter list is this? Is this the actual or the formal? That's the formal parameter list, right? And what do you know? And so here, down here in another part of the program, in another part of the translation unit, whenever you might have something like J gets my function. I don't know. Like let's say 5 and 4.7. Right? Now, what parameters are these? Actual or formal?
Actual.
They're actual. And so the 5 corresponds to this, and the 4.7 corresponds to this. And these are called by what? Called by reference or called by value?
Called by value.
Called by value. So it's legal to have these constants here, right? Now, what would happen in a program like this, if you were writing a program like this, and what would happen if you did this? Instead of saying my function 5, 4.7, what would happen if you said my function 5, just like that?
An error.
That would be an error. Why would it be an error?
Because my function takes 2 parameters.
Yes. Yeah. Now here's the thing. If you go through this, these are examples of statements that you can parse with this subset of C++, the grammar in the book. If you go through and actually do this and actually parse this, according to the rules of production, this will actually pass. I mean, it will appear as if this is valid, because there's nothing in the rules of production that say the number of parameters here of formal parameters has to match the number of parameters here. There's no way for that grammar to say that, and it doesn't say that. In fact, do you see what this is? I mean, do you remember that? Do you remember that context sensitive grammar that we had? What strings did it produce? Remember that little nonsense one?
B, B, C.
Yeah, it produced things like A, B, 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 C, C, C. And what did this grammar do? What did this grammar enforce? It enforced the fact that what?
However many A's there were, there's the same amount of B's.
Yeah, however many A's there were, that's how many B's, and that's how many C's. Well, see, but this grammar does not enforce the fact that however many actual parameters there are, that's how many actual formal parameters are, that's how many actual parameters there are. This grammar doesn't enforce. In order to enforce that, what kind of grammar would it have to be?
Context.
It would have to be context sensitive. See, it's like this was. So here's the point. The point is that even though, and this is typical, even though there are rules for what makes a legal sentence in the language, even though there are rules that would actually make the language itself be context sensitive, to have a context sensitive grammar, to have the parsing in the compiler be based on a context sensitive grammar would be way impossibly complex. Just way, way impossibly complex. So what is always done in practice, is the grammar is always context sensitive, and then what they do is the compiler has to have an extra check.
You mean context free?
Sorry, did I say?
Yeah.
Sometimes, yeah, okay. So the grammar is always context free, right? The grammar is always context free, okay? And then what happens is after the compiler actually compiles it and it's correct according to the grammar, then after it figures out that it's correct according to the grammar, then it goes back and it inspects how many parameters there are here and how many parameters there are here, and it makes the check separately from the grammar. And that's where it detects the error, that this is illegal. Do you see what I mean? But that determination is outside the grammar. That's after the whole thing has been, because if it passes the grammar, if it passes the grammar test, then it's okay according to the grammar. But then after that, it adds on its own further checks to make sure that this rule is not violated. So do you see what I'm saying? The point is that the language itself is context. The C++ language is a context-sensitive language, but we use for practical purposes, we use a context-free grammar to do the parsing. Is everybody clear on that? So I might ask you a question with a subtle distinction there, and so just remember that. Okay, so now what we're going to do is we're going to learn this other way of specifying a language, and it's with finite state machines. So now, it sounds like you guys have already done finite state machines before. So maybe some of this is reviewed to most of you. But for completeness, let's go ahead and work through the definition. So, okay, first of all, a finite state machine consists of a finite set of states called nodes. Those are represented by circles. And then there are transitions between the states represented by directed arcs. And now here's the thing. Each one of those, what's the first part of a grammar?
Non-terminals.
Non-terminals, and the second part is
Terminal.
the terminals. Okay, so now the terminal characters are the ones that you actually see, right? Mm-hmm. So the arc in a finite state machine is labeled by a terminal character, not by a non-terminal, but by a terminal character. So these are the ones that you actually see. And then one special state is designated the start state, and this roughly corresponds to the start symbol in a grammar. And then we have a non-empty set of states are designated by the final state, are designated the final states. And the way we normally denote those is we put a double circle. All right, so here is our first example of a finite state machine. I think I'm going to draw this just so I can. So here's A, so we can, and then here is C. And, okay, so now, first of all, the way you represent the start state in a finite state in this diagram is it's the one that has the arrow coming into it that comes from nowhere. All right. So this indicates that this is a start state. And the way you represent a final state is a circle with a double ring around it. I mean a node with a double circle, right? So A is the start state, B is the final state. You can have more than one final state, and we will eventually. And then here's another state. And then the transitions between them. So with this machine, there's a transition from A to B on a letter. And then there's a transition from B to B on a letter. And then there's a transition from B to B on a digit. And then there's a transition from A to C on a digit. And then there's a transition from C to C on a digit. And from C to C on a letter. Now here's how this thing works. This is a finite state machine that recognizes an identifier. Now do you remember how we did a grammar that represents an identifier before, right? You remember that one? What's an identifier? What's the rule for an identifier? Didn't we have
The letters and digits?
Yeah, and the first one has to be a what?
A letter.
Oh.
The first one has to be a letter. Right? Didn't we do the grammar for that? I thought maybe not.
I don't think so.
We didn't?
I feel like we did.
Actually, wasn't it here? Wasn't it on this? Here, I thought it was one of the last ones here on figure here.
Yep, that one. Yep.
Figure 7.8 over here. An identifier is either a what?
A letter.
A letter, or it's a what? Identifier followed by a letter, or it's a what? Identifier concatenated with a digit. So there's 3 rules of production. Yeah?
So,
But now my claim is that this is a finite state machine that actually does the same, that recognizes an identifier in the same way that grammar does. Now, now here's the question. We haven't said how this works. I'm just making this claim that it's like this. So now here's the question. How does it work? The way it works is like this. So you use your imagination. You know how you imagine that this is a little model railroad. And this is a track. And you have the engine that comes in from the front. And what happens is the engine comes in here, and every time it hits every time it's at a state, the next time it goes, it takes one of these two things. It goes one of these two places, and it just keeps going and going and going. And every time it makes a transition, it makes a transition on a terminal character, right? And then when it stops in a final state, that string of characters that it ran over on those things, that string of characters is a valid sentence in the language. Do you see what I mean? Mm-hmm. So here's we imagine. So here's our little train. So here's the conductor. Okay? And here's, so he's coming along here, right? And so now let's imagine how he goes. So let's say he goes here. So let's say he goes here, and he goes over this letter. So that's like A, and then he goes over this letter back to here. So he goes from this letter, he gets at B. Then he takes this, and that's another letter. So let's say that's, C, and let's say that's D, and then let's say he goes over this digit, and that's like 5. So then what that means is that, now I don't remember the letters I see. A, C, D, 5. And because we wound up here, because we ended up here in this final state, that proves that A, C, D, 5 is a valid identifier. Are you with me?
right. Yes.
All right. Now, and then, okay, so this finite state machine proves that ACD5 is a valid identifier. But now here's the thing. I don't think I'm not sure if we defined this term before, but have we defined the term parsing?
No.
Okay. What does it mean to parse a sentence?
It's to go backwards. So to verify its validity.
Right, so what happens is the parsing problem is not to generate a random valid sentence in the language, but it's given a string,
Assess its validity.
right. Mm-hmm. And so the question is, how do you parse an identifier using this finite state machine? So here let's do it like this. Let's suppose we say 71S, and we want to parse this. So the question then is, how would that work? How would we determine if 71S is a valid one? Okay, so now I got to erase all this green stuff. All right. So here's how we would try to parse 71S with this machine. We would come along here, and we're at A. Well, 7 is not a letter; it's a digit. So we would come along here, and we'd go to digit, and then 1, that's a digit, so we'd go around here, and then S, that's a letter, so we'd go around here. Now, in the end, where did we wind up? What kind of a state did we wind up in?
Non-terminal.
Well, no, not the terminal. What's it called?
A non-accept state.
It's not a final state.
Final state. It's not a final state. If you wind up and it's not a final state, then what happened?
It's not valid.
This is not valid. But if you take it, so basically what you're doing is the engine is starting off here, and you have what you're doing is you're scanning your string from left to right. Are you with me? And each time you go to the next one, you see which road to take on the finite state machine, and you go and you go and you go, and then in the end, when you get to the end, boom, the question, if you're in the final state, then it's a valid string sentence in the language, and if you're not in the final state, then it's not. Okay, question?
Where is the need to have that bottom option at all? The option of having a digit first.
So that we'll know where to go on each one of these.
Couldn't we just go along and see that the first one's a letter and you'd automatically just say no?
That is a really good point. And so let's hold that thought for just about 2 minutes.
Okay, I will hold it.
Maybe 3. All right. So before we go there, let's take a look at what the parsing rules are. The parsing rules then for a finite state machine like this is you start at the start state, you scan the string from left to right, and for each terminal scanned, you make a transition to the next state of the FSM. FSM is an abbreviation now for finite state machine. By the way, why do we call this a finite state machine?
It results in the final state.
No, finite. Not final state machine, it's finite state machine.
Because there aren't unlimited states?
Yes, because there's only a finite number of states. How many states do we have here? 3. 3 is finite. Are you with me? So we're not talking about infinite state machines, which is a good thing because nothing in this world, there are no computers that have infinite memory. You know, there's no, infinity doesn't exist in all real machines. It's all finite, a finite number of states. Okay, so for each terminal scanned, we make a transition to the next state in the FSM, in the finite state machine. And then after the last terminal is scanned, if you're in a final state, the string is in the language, otherwise it is not. Now, hold that thought for yet another minute, because now what we want to do is see, this is the way we draw a finite state machine, and this is a really good way to visualize it. But how can we do this textually, with text, instead of with a picture? Because this picture has arcs and arrows and da-da. And so it's kind of hard to put this picture in a computer and have these, you know. So what's another way to represent this finite state machine? Well, another way is with a table. Table? Are you with me? And this is called a state transition table. Okay, so figure 7.11 is the state transition table that corresponds to this finite state machine. So here's what we do. We list on the leftmost column, we list the current state. And this, we have 3 states here, A, B, and C. So we list the states, A, B, and C. We put a little arrow drawing into A. That indicates that A is the start state. Are you with me? We put a circle around B. Now this, we just put 1 circle around B. It's 2 circles here, but we only need 1 circle because we don't put circles around the other ones. Are you with me? So B is the final state. Is everybody clear? And then what we have in the body of the table, what we have is for every possible terminal character, we say what the next state is. So do you see on that first row, if the current state is A and we scan a letter, the next state will be B. Are you with me? So that corresponds to if the current state is A and we scan a letter, the next state is B. Now does everybody see how that corresponds directly to this? Are you with me? Mm-hmm. So this is the state transition diagram. That is the state transition table. And obviously, why is it called a state transition diagram? Because we're making transitions from one state to the next on that with the arrows here, right? Now, what did you say we could do?
Get rid of state C.
Yeah. Now, and so what you are proposing, in fact, is what we're going to call a simplified finite state machine. Okay. Because really, when you think about it, this state C, really its only purpose is to give us a place to go to when we're scanning. But it would be more efficient. It's actually an efficiency problem too, right? Mm-hmm. Because if we know right away that the first one is not a letter, then we can stop scanning. Yep. And we don't even have to go. We know right away. So for efficiency purposes, it would take less processing to discover that it's not correct. Right. If we got rid of this. So that's what we do with a simplified finite state machine. So now what we are proposing is that for a simplified finite state machine, not all states have transitions on all terminal symbols. All right? So here's what we're going to do. Over here, we're going to actually erase this. this one. We'll just get rid of it. All right? We're just going to get rid of it. But now wait a minute. If we get rid of it, now see, here's a little nicer drawing, this next figure here. So does everybody see that this is the figure with the C gone, right? And everything else is the same, right? Now we only have two states. But now wait a minute. Now our rules have to change. Because what are the rules for a full finite state machine, a not simplified?
If you end in a final state, when you're parsing.
Yeah, when you're parsing. If
after the terminal.
After you scanned the
last terminal scanned, the final state of the string is in the language. If you are in a final state, then the string is in.
So how can you fail?
By ending in
a state that is not a final state. But now there's not just one way to fail. With a simplified machine, there's not just one way to fail.
Mm-hmm.
There's what? There's two ways to fail. Are you with me? So it still might be possible with a simplified finite state machine to run out of input and to not be in a final state. So that's still one way to fail. But another way to fail now is what? You may be in some state and the next input character does not correspond to any of the transitions from that state. Are you with me? So you got to change the rules for how to do the parsing. And you have to add this additional rule. Okay? So here's the picture of the simplified finite state machine. But now I've got a question for you now. What is the table? This is the state transition what? Diagram. What is the state transition table going to look like for this?
It's gonna have only 2 lines.
It's only going to have 2 lines, but there's something else. And there will be an arrow into the A, right? And there will be a circle around the B. But now, what about the body of the table?
It'll say in the column that says digit, in the row that says A.
In the column that says digit, in the row that says A.
It will say.
Well, yeah.
Or blank.
It'll just be blank.
Mm-hmm.
Yeah. And you see why?
Mm-hmm.
Because there is no transition from A to digit. Sorry, there is no transition from A to another state on digit. Yeah? Okay. So we've got 2 kinds of machines now. We have a full finite state machine and we have a simplified finite state machine. Now there is a third kind of a finite state machine. And that's this. Do you guys like choices? Do you guys like free choice?
Yes.
So do I. I think the more choice, the better. Okay, so now how could we have a choice? Suppose, there's some finite state machine, blah, 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 all over the place. And suppose that we are in this state right here, okay? And how could we have choice?
We could have a letter on both there.
Yeah, whatever character. We could have, whatever the symbol is, there's nothing to prevent us in our drawing from having, if we're in this one state here, in having a transition from the same thing, right? Do you see what I mean? So such a machine is called a nondeterministic machine. Why is that? That's because when we're in this state, it's not determined which way we'll go when we do the parse. So therefore, it's non-deterministic.
Would most machines be non-deterministic?
Well, we'll get to that. Hold that thought for another few minutes, and we're going to come back to that.
Would it go through the entire thing testing in one?
Yeah, we're going to have to. Yeah, that's a good. Actually, let's talk about that now. Okay, so here's the problem. The problem is, as we're parsing a string, and when we get to a state where we have a choice of where to go, what we do is we just pick one, and we go there, right? Mm-hmm. Now, if we pick one and we go that way, and then when we're at the end, we are in a final state, what have we done? What have we determined?
That's right.
That it is valid. But what if we pick this way and we get to the end, and when we get to the end, we're not in a final state? Or perhaps later on, we ran into a state for which there is no transition from it on that next input character. Then we have not determined that it's invalid. Why not? Because we might have been able to prove that it's valid by backing up and going this way. So which one is harder, would be harder to program, a deterministic or a non-deterministic? Yeah, it'd be harder to program, but you could do it. Not just maybe, I think you could. But you'd have to have some way to go and try and back up and then try the next one, you know. Are you with me? Yes. So the rules, so now with a non-deterministic machine, the rules now are a little bit even more complicated. So here's the rules. First of all, the definition of a non-deterministic finite state machine. At least one state has more than one transition from it on the same character. Okay? That's what makes it non-deterministic. And furthermore, if you scan the last character and you are in a final state, you know the string is valid. Right? Does that make sense? Mm-hmm. On the other hand, if you scan the last character and you are not in a final state, the string might be invalid. You haven't proved that it's invalid, because what if you just took the wrong fork in the road earlier on? And not only that, but there might be several forks in the road, in which case, you know, you'd have to back up to the first fork and try that, and then if none of those work, you might have to back up to the previous fork and then try all those. You see what I mean? So, okay. So if you scan the last character and you're not in a final state, the string might be invalid. To prove that it's invalid, what must you try?
All possibilities.
All possibilities with backtracking.
That's a new term.
Well, you understand what we mean by
Yeah.
backtracking, okay? Now, but to show you that this is actually non-deterministic finite state machines are actually useful, here is an example in figure 7.14 of a non-deterministic finite state machine that I think you can see recognizes a possibly signed integer. Right? And didn't we do, I think we had a grammar that recognized the signed integer before too.
Yes.
Okay, so this
is the DDDD.
Yeah, this is with either plus or minus,
or the empty string.
or yeah, okay,
Or the
empty string. Yeah. This one doesn't have an empty transition on it. We're going to get to that in a minute. Okay, so let's take a look at how this machine works. Okay, so first of all, we start at state A, and I don't want to draw this, but I think you can imagine now that we've done one with a little railroad car engine. Okay, so let's try to parse plus DD. Okay, so here's the string that we're trying to parse, plus DD. And let's see if we can imagine the transitions. Okay, so suppose we come in and we start at A, right? Now suppose we take that diagonal up to C. Oh no, we can't, because it's a plus. Sorry, we have to take what? We have to take the plus to state B, right? And now let's suppose we take the up arrow to C. Now what happens? Now what happens? We are here on this parse, right? So here, we took the plus to state B. On this D, we went from B to C. Now at this point, what did we discover?
We're done.
Well,
It's invalid.
we discovered that it's invalid because there's no transition from, well, it might be invalid because there's no transition from C on this D. Are you with me?
Yes.
Okay, so what do we have to do? We have to back up. So let's try, so we must have made a wrong transition. So the plus will get us to B. Now what? Suppose we take from B to B on this.
And B to B again.
And now suppose we take B to B on this again. Darn, that's wrong too. Everybody's visualizing this? So what's the right way to do it? But we can still do it though.
ABC.
A, to state B to state C, and now we're out of input characters, and we're at C, and it's the final state, so therefore it's valid. Does everybody see how that works? And you can imagine other scenarios. I won't go through any more examples, all right? Is everybody clear on how that works? Now my question is, now what is this? The state what? State transition diagram. Now my question is, what does the state transition table look like for a non-deterministic finite state machine?
It'll have multiple options in the columns.
It'll have multiple options in the body. Okay? So now, do you see here in figure 7.15, what's interesting about this state transition table? Well, not only are there some entries in the table that are blank, that means it's what?
It's not a final state.
It's simplified.
It's simplified. That means it's simplified. We have to have that extra rule. Okay, but now what else do we see? If we're in state A and we input a digit, we can go to either what?
B or C.
State B or state C. And if you look here, if we look back here, what did we say? If we're in A and we have a digit, we can go to B or C. So here, if we're at A and we get a digit, we can either go to B, that's the bottom one, or C, that's the diagonal one.
Mm-hmm.
Yeah? So there is your state transition table for a simplified, non-deterministic finite state machine. All right, and now the next concept is the concept that corresponds to the empty string in a grammar. With a finite state machine, we have a possibility that is called not an empty string, but an empty transition. Okay. Now here's what an empty transition does. An empty transition allows you to go from one state to another state without scanning any characters at all. That's what an empty transition does. And one little side note here also. All finite state machines with empty transitions are considered to be non-deterministic. And why is that? That's because if you're at a state and there's an empty transition from that state, you can always choose to do what? Either take one of the other transitions and scan the next character, or
Stop.
or take the empty transition and not scan. See, so that's basically a choice. That you always have a choice when you have an empty transition. See, for example, here, suppose we're in this state and we have an empty transition to this state, and we have, like a D to this state. And suppose suppose we're like plus D, and suppose we are right here in our scan. Well, hey, there's a D here, right? But there's an empty one here. So there's two choices. I could either be here and on this D go like this, or I could be here and on empty stay here. So that gives me a choice. You see? So anytime you have an empty transition on a finite state machine, that finite state machine is kind of like, by definition, it's non-deterministic. We consider it to be not, because it automatically gives you a choice. When you have this, when you have a transition with D, it automatically gives you a choice of either scanning this or not scanning it and staying it and going to the next one. See, going to another one.
Okay, so imagine that the empty transition, the state that it's in had a loop to itself with another empty transition.
Yeah, then that's a special case.
And it was a final state. Could you just consider pretty much anything valid if we got to that point?
No, well, it depends on if you ran out of characters.
So
Because see, when you do the empty transition, you don't scan a character.
Right.
You go on the empty one.
Okay, so you have to finish.
You have to finish scanning and wind up in a final state. Are we good? Mm-hmm. Now look, here's why the empty transition is here's a situation where the empty transition can be quite useful. Figure 717 shows is another little variation on a theme. And look, you guys, how slick this is. This recognizes, our old friend, the signed number. Like, it could be like plus D, 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 or it could be minus D, D, or it could just be D, D. Right? So look, so what's the rule? The rule, kind of like informally in English, is a signed number could have a single plus, or it could have a single minus, or it could have nothing. So do you see that translates directly to the transitions that go from I to F? See? So if we're at the start, we could have a plus and go to F. Or we could have a minus, a hyphen character, and go to F. Or we could have the empty transition and go to F. See? And then once we are in F, what do we have to have? At least one digit. So in other words, this is not a valid signed integer. Right? We have to have at least one digit. So that's the transition from F to M on digit. And then we can have any number of digits after that. And so we have digit, digit, digit on M. Now, you guys, what is this? The state transition diagram. What would the state transition table look like for a finite state machine that has an empty transition? It will have a column for epsilon, for the empty transition. And so, here it is. Now, I ask you a question. Is this deterministic or non-deterministic?
Non-deterministic.
It's non-deterministic. It doesn't have those double things in there, but because it has the epsilon, it's non-deterministic. So now here's the next thing we want to do. Given that it's easy to write, it can be useful, it can be helpful to write down an initial finite state machine with an empty transition in it like this. But by the way, what did we say would be easier to program? A deterministic or a non-deterministic?
Deterministic.
And this is non-deterministic. And do you see that it would be kind of difficult to program this up?
Because you couldn't know.
Because you wouldn't know at one point, you wouldn't know if you should go, and you'd have to try it and backtrack. So what we want is a procedure for eliminating the empty transition. Any machine that has empty transitions in it can be transformed to an equivalent machine with the empty transitions removed. I don't know if you guys have learned how to do this yet in automata theory. Okay? So here it is. So this is a little bit of review for those of you who have done this before. Now think about this. Let's suppose that we are here at this state A, and let's suppose that we could go here, suppose letter B will take us to this state, to state big B, and let's suppose that, and let's also suppose that the empty transition will take us here, and then let's suppose that D will take us to state capital big C. Actually, and let's suppose that little e, and now let's make this F, and let's suppose that little f will take us to state big D. All right? Let's just imagine, and then there's more, there's ... and there's more, ... This is all just part of a big finite state machine, right? Now, all you have to do is just think about this, and it all makes perfectly logical sense. So, and we have this string that we're scanning. So suppose that we've done some things like, like X, Y, and here we are with B. and something like this, and then dot, 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 okay? And so let's suppose that in our scan, we are right here, okay? Now, you guys, watch this. What are our choices here? Our choice is we could take little b, we could scan this little b and go to state big B, right? But another choice is to do what?
Epsilon.
Is to stay right here and take epsilon from here to here. But if we do take, actually let me make this be D. Okay. Another choice is to take, so we are here. So now my first instance isn't quite right because this is a D. But I mean, we are here. We see this one transition is on B, but now we don't have a B, we have a D. So what should we do? We should take epsilon from here to here. That will get us to B, right? And then we can do what? Take the D from here to here. Are you with me? So wait a minute. Do you see that then? How do you see what we should do?
Just take out the empty and put a direct line with a D from A to C.
Yes.
Couldn't we do that from D to F? A to B?
Yeah, right. Yeah. But your observation was absolutely correct. What we would do is, because we can take an empty transition from here to here and then go on a transition on D from here to here, we can, if we eliminate this, we can make the transition go from here to here directly on what?
D.
On D. Are you with me? Mm-hmm. But on the other hand, what if this were an F?
Then we can do the same thing going to the big.
Yeah, so not only do we, if we eliminate this, not only do we have to put one going from here to here on this D, we also have to go from where to where?
A to D.
From here to here on what?
F.
On F. Now, does everybody see that? Mm-hmm. And not only that, you guys, but we've ignored something about final state. I mean, see this with this one that we just did, neither C nor D.
Well, if B was a final state, we could have made A a final state instead, like that.
Well, here.
Assume B was a final state.
Because then the epsilon would be going to a final state, so it would end. So instead, we could have just made A a final state.
Right. If B was the final state, then we could have gone to B, making no transitions, and that would have made, and so therefore A would have to be a final state. So that's the other requirement whenever you remove the empty transition. Okay, so here it is. Given a transition from P to Q on the empty transition, and from Q to R on A, you add a transition from P to R on A. That's what we just did. And then if Q is a final state, you have to make P a final state also. Okay, so so now here's another example. We did one example here, here's another example. So do you see here the original finite state machine? If you go from X to Y on the empty state, on the empty transition, and then you go from Y to Z on A, when you remove the empty transition, you go from X to Z on A. Does everybody see that? Mm-hmm. Okay. And here's this one, the one that we did before. Are you with me? You eliminate that empty transition, so that gives us the digit to M and the digit, right?
Right.
Are we good with that? And now here's yet another example that shows the final state one, the final state example. So here, if you go from W, figure 7.20, if you go from W to X on the empty transition, well, if you're going to eliminate that transition, you have to be able to go from what? From W to A, are you with me? And from you have to be able to go from, you have to be able to go from W to Y on A, right? Because we're going from X to Y on A. And we also have to be able to go from W to Z on B, because we're going from X to Z on B. X to C. And then, and then because X was the final state, and we had an empty transition to that, that means W has to be a final state, because we could go from W to X on the empty transition and be a final state. Yeah? So for your homework assignment for next time, there are a bunch of finite state machine exercises. All right? Some removing empty transitions. And there's also a slightly more challenging one, that is to actually design a finite state machine to recognize a certain pattern. Those are trickier, because those are design problems. What we're doing here is we are doing analysis problems. But what you're going to have to do for your here, let me end with this final comment of where this all fits into your project. As it turns out, to write a translator with a grammar is unnecessary for your project. Your project is going to be simple enough to where your parsing is all going to be based on finite state machines. So one of the things that you are going to have to do for your project is you are going to have to design your own finite state machine. So this exercise of designing a finite state machine to do something is similar to what you're going to have to do with your own project. Are you with me? That's how it's going to fit
Write the
it.
assembler.
Yeah, when we write our assembler. That's why we're jumping ahead here, is so that we can learn how to implement finite state machines, because they will be part of your assembler. Your assembler is going to be based on finite state machines.
Okay.
So we're going to have to learn how to program them. Yeah? It's a beautiful application of theory to practice. Because all of this is this mathematical theory of finite state, but now we're actually going to use it. You're going to build one of these into your program to do the translation. It's really neat. All right? So good deal. See you on Monday.